Chapter 1, Introduction to Nuclear Magnetic Resonance, NMR, Spectroscopy, fleshing out the content for each section. Chapter 1, Introduction to Nuclear Magnetic Resonance, NMR, Spectroscopy. Chapter Objective, to establish the fundamental physical principles that underpin all NMR experiments, providing the necessary theoretical background for understanding practical operation of the AV3 spectrometer. 1 The physical basis of NMR, spin, magnetic moments, and polarization. The nuclear spin. Certain atomic nuclei possess an intrinsic property called spin, quantified by the spin quantum number, I. Nuclei with I is not equal to 0, e.g., \1h \13c \19f \31p I equals 1/2, behave as tiny magnetic bars. The magnetic moment, mu. A spinning charged particle generates a magnetic field, resulting in a magnetic moment. This vector defines the strength and direction of the nucleus's tiny magnetic field. Polarization in a static magnetic field, B. When placed in a strong, external, static magnetic field, B, provided by the superconducting magnet, these magnetic nuclei can adopt specific orientations. For nuclei with I equals 1/2, there are two possible energy states, one low energy state, alpha. The magnetic moment is aligned with the B field. 2 high energy state, beta. The magnetic moment is aligned against the B field. The energy difference, delta E, between these states is directly proportional to the strength of B. The Boltzmann distribution. At thermal equilibrium, there is a slight excess of nuclei in the lower energy state, typically a few parts per million. This population difference is the source of the NMR signal. A stronger magnet, higher B, creates a larger population difference and a more sensitive instrument to the Larmor precession and resonance condition. Precessional motion, the magnetic moments of nuclei do not simply align with B, they precess around the direction of the B field. This motion is analogous to a spinning top precessing in the Earth's gravitational field. The Larmor frequency, nu. The frequency of this precession is called the Larmor frequency. It is uniquely defined for each isotope at a given magnetic field strength by the Larmor equation, omega equals gamma B, where omega is the Larmor frequency, in radian/second, often given as nu, in hertz. Gamma is the gyromagnetic ratio, a unique constant for each nuclide, e.g., gamma 4\1h is large, 4\13c it is 1/4 that of \1h b is the strength of the static magnetic field, e.g., 94t, 141t, etc. The resonance condition, NMR, occurs when nuclei are irradiated with radio frequency, RF, energy that matches their precise Larmor frequency. This is the resonance in NMR. Applying an RF pulse at frequency nu causes nuclei to absorb energy and transition from the low energy to the high energy state, a spin flip. This absorption of energy at a specific frequency is the fundamental event that is detected. 13 Relaxation phenomena, T and T return to equilibrium. After an RF pulse disturbs the equilibrium state, the spin system must return to it. This process is called relaxation. T relaxation, spin lattice, longitudinal, relaxation, process, the process by which excited spins release their energy to the surrounding environment, the lattice, other molecules, solvent, etc., and return to the lower energy state. Effect, recovery of the net magnetization vector along the n-z axis. The direction of B governs the delay needed between successive scans for accurate signal integration, especially important for quantitative NMR. T relaxation, spin, transverse, relaxation, process, the process by which excited spins exchange energy with each other, causing the NMR signal to decay. It is a loss of coherence, synchronization, among the precessing spins. Effect, the decay of the observable NMR signal, the free induction decay, or FID, in the XY plane governs the natural line width of NMR signals. Shorter T times give broader peaks. T is always less than or equal to T14. The Fourier Transform, FT, NMR experiment. The time domain signal, FID. The NMR spectrometer does not detect a nice spectrum directly, it detects a decaying, oscillating electrical voltage called the free induction decay, FID, which is a signal in the time domain, the frequency domain spectrum. The actual NMR spectrum we interpret is a plot of signal intensity vs frequency, the frequency domain. The role of the Fourier transform. The Fourier transform, FT, is a mathematical procedure executed by the spectrometer's computer that converts the complex time domain FID into the familiar frequency domain spectrum, the pulse acquire FT workflow. This is the basis of all modern NMR experiments on the AV3. One pulse, a short, powerful burst of RF energy tips the net magnetization to acquire. The spectrometer listens and records the FID as the spins press S and relax 3 feet. The computer processes the FID using the FT algorithm to produce the spectrum. 15 Overview of NMR applications in chemistry and biochemistry. Structure elucidation. Primary application: determining the covalent connectivity and stereochemistry of organic molecules, natural products, and novel compounds. Chemical analysis. Identification, acting as a fingerprint to confirm the identity of a known compound. Quantification, QNMR, determining the purity or concentration of a compound without a calibrated standard. Reaction monitoring, tracking the progress of chemical reactions in real time. In situ NMR, biomolecular NMR, determining the 3D structures of proteins and nucleic acids in solution. Studying molecular dynamics, folding, and interactions, e.g., drug-protein binding. Material science, studying polymer composition, dynamics, and morphology. Medical imaging, MRI, in vivo application of NMR principles to create detailed images of the human body. Chapter 2, the Bruker AV III NMR spectrometer, an overview. Chapter 2, the Bruker AV III NMR spectrometer, an overview. Chapter objective, to provide a high-level understanding of the major hardware and software components that constitute a modern Bruker AV III NMR system and how they work together to conduct an experiment. 21 System architecture, console, magnet, and workstation. The Bruker AV III system is a fully integrated instrument comprising 3 main physical units that work in concert. 1. The magnet, function, provides the strong, stable, and homogeneous static magnetic field, B, which is the foundational requirement for NMR location. Typically housed in a separate room or shielded area due to its strong stray field and sensitivity to environmental disturbances. Key feature, houses the probe head and sample within its bore. 2. The console, AV3 function, the electronic heart of the system. It generates the radio frequency, RF, pulses to excite the nuclei, receives the tiny NMR signals from the probe, and digitizes them for the computer. Location, sits in the spectrometer room, connected to the magnet via a bundle of cables. Key feature, a modular system where boards can be added or upgraded to enable experiments on different nuclei, e.g., adding a second carbon channel for H/C/N probes. 3. The workstation, function, the user interface. It controls the console, processes the acquired data, and stores all experimental parameters and results. Location, typically located in a nearby control room. Components, a standard computer, often a Linux PC, running the TopSpin software suite. Data flow, the user inputs commands in TopSpin on the workstation sends digital instructions to the console generates analog RF pulses and sends them to the probe in the magnet. The probe delivers the pulses to the sample and receives the resulting NMR signal. The signal is amplified and digitized in the console. The digital data, FID, is sent back to the workstation. TopSpin processes the FID into a spectrum for the user to analyze. 22 magnet types, superconducting magnets and field strengths. Superconducting technology, principle, the magnet solenoid is made from a niobium tin or niobium titanium alloy. When cooled to near absolute zero, 42 K, by liquid helium, it loses all electrical resistance, allowing a current to flow perpetually without any power input, creating a persistent, stable magnetic field. Implication, once charged or ramped to its field strength, the magnet remains on indefinitely, 4 years, provided it is kept cold with cryogens. Field strengths and nomenclature. Field strength is measured in Tesla, T, or Historically, in proton-Larmor frequency, megahertz, common AV3 systems include 400 MHz, 94 T, 500 MHz, 117 T, 600 MHz, 141 T, 700 MHz, 164 T, and 800 MHz, 188 T, and higher field advantages, 1 increased sensitivity, signal-to-noise ratio, S/N, increases approximately with B, 7/4, to B superscript 2 increased resolution, the separation between signals, chemical shift difference in Hertz, increases linearly with B, making overlapping peaks easier to resolve. Shim system, to ensure field homogeneity, the magnet contains a set of shim coils, Z1, Z2, X, Y, XY, etc. These are adjustable electromagnets that correct for tiny imperfections in the main magnetic field, which is critical for obtaining narrow spectral lines. 23. The Avenue 3 console, key components and data flow. The console is a rack of modular components. Key modules include synthesizer, SY. The master clock generates a very stable and precise reference frequency. Generator, FG, creates the specific RF frequencies for each channel, e.g., one for superscript 1H, another for superscript 1 superscript 3C, based on instructions from the SY pulse shape generator. PSG defines the precise timing, duration, and power level, shape, of the RF pulses, enables selective pulses and complex multi-pulse sequences. RF amplifier, TX takes the low power pulse from the PSG and amplifies it to high power, e.g., 50W, 300W, for transmission to the probe duplexer. DUX, a critical electronic switch inside the probe that protects the sensitive receiver from the powerful transmitted pulses. Preamplifier, preamp, located very close to the probe, it receives the extremely weak NMR signal, microvolts, from the probe and provides the first stage of amplification with minimal added noise, crucial for sensitivity. Receiver, RCU, further processes the signal from the preamp, including filtering and conversion from an analog voltage to a digital number, analog to digital converter, ADC. 24. Introduction to TopSpin software. The NMR operating environment. TopSpin is the comprehensive software environment for controlling the AV3 and processing data. The main interface, divided into several key panels, command line, for entering text commands, e.g., lock, RGA, ZG, NMR status panel, shows real-time information like lock level, temperature, and sample position. Plot windows, for displaying spectra and FIDS. Parameter panel, where all acquisition, ACUs, and processing, PROCs, parameters are set and viewed. Core functions, 1. Acquisition control, all commands for locking, shimming, setting up experiments, and acquiring data are executed here. 2. Data processing, includes Fourier transformation, phase correction, baseline correction, integration, and peak picking. 3. Data analysis, tools for plotting, multiple spectrum comparison, and structure assignment. For automation, the Icon NMR module allows for queuing samples and experiments to run unattended. 5. Database, stores all experimental data, parameters, and processing history for each sample. The Prosperity, ProSol, database, a key feature integrated into TopSpin. It contains pre-calibrated pulse widths and power levels for standard experiments on Bruker probes. The getProsol command automatically fetches these parameters, ensuring experimental setups are quick, easy, and reproducible. Chapter 3, the Magnet and Cryogen Handling. Chapter objective, to provide a comprehensive understanding of the superconducting magnet system, focusing on the critical procedures for safe cryogen handling, the hazards involved, and the protocols for managing the magnet state. This chapter emphasizes that safety is the paramount concern when working with this hardware. 31. Magnet safety, quench hazards and emergency procedures. What is a quench? A quench is the sudden loss of superconductivity in the magnet coil. This causes rapid resistance heating, which boils off the liquid helium coolant extremely rapidly, converting it into a large volume of gaseous helium. Causes of a quench can be spontaneous, very rare, or initiated by training emergencies, A person with a metallic implant, e.g., pacemaker, aneurysm clip, entering the 5 gauge line, physical shock, sharp impacts to the magnet or dewar, internal failure, a fault in the magnet coil or joint, cryogen depletion, allowing the helium level to run too low, causing the coil to warm up. Hazards: 1. Asphyxiation. The primary danger: helium gas is inert and will displace breathable air in the room. A full magnet quench can release thousands of liters of gas in seconds. 2. Cryogenic burns. Contact with venting cryogenic gases or cold surfaces. 3. Physical damage. The violent force of the venting gas can damage ceiling tiles, light fixtures, or other objects in the vent path. 4. Damage to the magnet. A quench puts immense thermal and mechanical stress on the coil. Emergency procedures. Immediately evacuate the room. Do not attempt to save data or shut down the console. Your safety is the only priority. Alert others in the vicinity as you leave. Do not re-enter the room until it has been verified that oxygen levels are safe. Using an O monitor, and the quench has completely finished. Know the location of the room's oxygen monitor and emergency ventilation controls before an emergency happens. 32. Cryogen management. Liquid nitrogen and liquid helium. Liquid helium, LH, BP equals 42 K/-269 degrees Celsius. Function: the primary coolant that keeps the superconducting coil at its operating temperature. Consumption: modern magnets have recondensing cold heads that dramatically reduce LH consumption. 0. Boil-off. Magnets can typically run for over a year on a single fill, only losing helium through minor permeation. Handling: extremely cold requires specialized transfer lines and personal protective equipment. PPE, liquid nitrogen, LN, BP equals 77 K/-196 degrees Celsius. Function: not used to cool the coil directly. It acts as a thermal radiation shield, drastically reducing the boil-off rate of the more expensive liquid helium. Consumption: LN typically requires weekly refilling, as it boils off much faster than LH in a closed system. Handling: less hazardous than LH but can still cause severe cryogenic burns. 33. Filling procedures for cryogens, manual and auto-fill systems, personal protective equipment. PPE mandatory: lab coat, cryogenic gloves, full face shield, and closed-toe shoes. No exposed skin. Liquid nitrogen, LN, fill, manual. 1. Check levels. Verify the LN level is low via the gauge or software. Alert. 2. Vent pressure. Ensure the dewar vent is not blocked. 3. Connect transfer hose. Securely attach the LN transfer line from the supply dewar to the magnet fill port. Never use force. 4. Pressurize supply dewar. Apply very low pressure, 1 to 2 psi, to the supply dewar to start the transfer. 5. Monitor. Listen for the characteristic crackling sound to change to a hiss, indicating the magnet dewar is nearly full. Watch the vent line for fog. 6. Complete transfer. Close the supply valve, depressurize the supply dewar, and carefully disconnect the transfer line. Liquid helium, LH, fill, typically by service engineer. This is a complex procedure due to the extreme cold and value of LH. It is almost always performed by trained field service engineers. It involves connecting a high vacuum jacketed transfer line and carefully controlling the transfer rate to prevent a quench from thermal shock. Operator role: to schedule the fill well before the helium level becomes critical and to provide access and assistance to the engineer. Autofill systems. Many modern labs are equipped with automated, bulk LN systems. These are connected to a large external tank and automatically top up the magnet when levels drop below a set point, eliminating the need for manual refills. 34. Monitoring cryogen levels and system pressure. Why monitor? To plan refills and to be aware of potential problems, e.g., a sudden increase in boil-off rate indicates an issue. Monitoring methods. 1. TopSpin software. The primary interface displays real-time levels of LH and LN, as a percentage, as well as the pressure inside the magnet dewar. 2. Physical gauge. A analog level meter, often a round dial, on the magnet top or console provides a hardware-based reading. 3. System pressure, must be kept within a specified range, e.g., 0.5, 15 bar. High pressure can indicate a blockage, low pressure can indicate a leak. Normal operating parameters. The manual for your specific magnet will list the safe level and pressure ranges. Familiarize yourself with them. 35 Long-term magnet shutdown and ramp down procedures. Shutdown vs ramp down. Shutdown, turning off the console. This is done daily and has no effect on the magnetic field. The magnet remains superconducting and at field. Ramp down, quenching the magnet. This is a deliberate, controlled process of shutting off the magnetic field. It is a major undertaking that should only be done for specific reasons, e.g., long-term facility shutdown, major repair, magnet relocation, and is performed by a trained service engineer. Reasons for a controlled ramp down: planned facility maintenance or renovation, the need to service the magnet's internal components, relocating the instrument to a new building. The process. Overview 1. A specialized device called a ramp box or dump resistor is connected to the magnet. 2. The engineer uses this device to slowly and controllably increase the resistance in the coil, converting the stored magnetic energy into heat in the resistor, which is dissipated in the boiling helium. 3. This is a slow process, several hours, to avoid the violent boil-off of an uncontrolled quench. 4. Once the field is at zero, the cryogens are fully evaporated and vented. 5. The magnet must then be carefully warmed to room temperature over a period of days to avoid thermal stress. Operator role: to plan this event months in advance with the facility manager and Bruker service. All samples must be removed, and all users must be notified of the extended downtime. Chapter 4, Probe Heads, Theory and Practical Handling. Chapter Objective: to provide a thorough understanding of the NMR probe head, the most critical and delicate interface between the sample and the spectrometer. This chapter covers the theory of its operation, the different types available, and the essential practical skills for its safe handling and tuning to prevent costly damage. 41 Probe Head Fundamentals, Tuning, Matching, and Q Factor. The probe head is the assembly that sits within the bore of the magnet and contains the sample. Its core function is to efficiently transmit RF pulses to the sample and receive the weak NMR signal. RF coil, a tuned circuit, like a radio antenna, inside the probe that is specific to a particular nucleus or range of nuclei. Tuning, the process of adjusting the probe's variable capacitors to change the resonant frequency of its RF coil to precisely match the Larmor frequency of the nucleus being observed, e.g., 60,013 MHz for superscript 1H on a 600 MHz magnet. An untuned probe delivers poor pulse performance and low sensitivity. Matching, the process of adjusting a second capacitor to maximize power transfer from the transmitter to the coil and from the coil to the receiver. A poorly matched probe reflects RF power back to the console, leading to poor sensitivity and potential damage to the electronics. The goal is to minimize the standing wave ratio, SWR, Q factor, quality factor, a measure of the efficiency and sharpness of the resonance of the RF coil. A high Q factor indicates a sharp resonance, which leads to higher sensitivity and better signal-to-noise ratio. A low Q factor indicates a broad resonance, which is less sensitive but can handle a wider range of frequencies, useful for broadband observed probes. Cryoprobes have an extremely high Q factor, which is a major source of their enhanced sensitivity. 42 types of probe heads: BBFO, QNP, TXI. Cryoprobes. Probes are specialized for different experiments. The AV3 console's flexibility allows it to work with any of them. Dual-channel probes, the most common modern workhorses. BBFO, broadband fluorine. Observe, a versatile probe where one channel is optimized for superscript 1H, high sensitivity, and the other is a broadband channel that can be tuned across a wide range of nuclei, including superscript 1F, superscript 3, superscript 1P, superscript 1, superscript 3C, superscript 1N, and many others. Ideal for multinucleus research. TXI, triple resonance inverse. The standard for advanced biomolecular NMR. One channel is for superscript 1H, observe, and the other two are typically tuned to superscript 1, superscript 3C, and superscript 1N. Inverse means it is optimized for detecting superscript 1H with the highest sensitivity, which is then correlated to superscript 1, superscript 3C / superscript 1N. Quadnucleus probe, QNP, a general-purpose probe where the observed channel can be easily tuned to the four most common NMR nuclei: superscript 1H, superscript 1F, superscript 3, superscript 1P, and superscript 1, superscript 3C. Less sensitive for superscript 1H than a Dedicated inverse probe but offers excellent flexibility for synthetic chemistry cryogenically cooled probes. Cryoprobes technology, the RF coil and preamplifier are cooled to 20 K, -253 degrees Celsius, using a closed-cycle helium cryostat. This dramatically reduces thermal electronic noise, the main source of signal degradation benefit, provides a 4x increase in signal-to-noise ratio compared to a room temperature probe, effectively reducing experiment time by a factor of 16. Handling, require a continuous supply of gaseous nitrogen for thermal insulation and have more stringent safety interlocks. 43 Probe head safety, handling and insertion/removal. The probe is fragile, incredibly expensive, and easily damaged. Proper handling is non-negotiable. Lifting, always lift a probe with two hands, one firmly on the body and one supporting the base. Never lift it by the cables or the upper collar. Insertion into the magnet, 1. Ensure the MA lift, if present, is correctly engaged and the probe is perfectly vertical. 2. Slowly lower the probe into the magnet bore, watching carefully to ensure it does not bind or catch on anything. 3. If there is any resistance, stop immediately. Do not force it. The most common cause is a forgotten NMR tube or debris in the bore. Removal from the magnet, 1. Use the MA lift to slowly and steadily raise the probe. 2. Once clear of the bore, secure it on its stand or a stable surface. Cable management, never let the probe dangle by its cables. Coil cables neatly, without putting stress on the connectors. 44 Tuning and matching the probe, theory and practical steps. When to tune/match, every time the sample, solvent, or nucleus is changed. Different samples and solvents have different dielectric constants, which detune the probe. The process using TopSpin, 1. Wob command. This command causes the console to wobble or sweep a range of frequencies around the target frequency and measure the reflected power to the display. 2. Sine wave patterns appear on the screen, 1 for tune, frequency, and 1 for match, power transfer. 3. Manual adjustment. Locate the physical tuning and matching rods or capacitors for the channel on the top of the probe. Know which is which before you start tuning. Adjust the tune capacitor to center the dip of the sine wave on the screen center line, frequency equals 0, matching, adjust the match capacitor to minimize the depth of the dip, bring it as close to the top of the display as possible. 4. Iterate, tuning affects matching and vice versa. Several iterations of small adjustments to both are usually necessary to optimize both parameters simultaneously. ATMA, automatic tuning and matching. Some advanced probes feature motors that allow TopSpin to perform tuning and matching automatically via the ATMA command. This is highly reproducible and minimizes user error. 45 Changing and handling NMR tubes to prevent probe damage. A broken NMR tube inside the probe is a catastrophic and extremely expensive event that requires a service engineer to disassemble the probe. NMR tube quality, always use high quality, straight tubes. Inspect them for cracks or chips before use. Filling the tube, the ideal sample height is 4 cm, covers the RF coil, never overfill. Excess sample can spill into the probe rotor and contaminate it, leading to poor spinning and shimming. Inserting the tube, 1. Wipe the tube clean with a lab wipe and solvent to remove any residue. 2. Use a depth gauge to ensure the tube is inserted to the correct height. 3. Place the tube in the spinner turbine and lower it gently into the probe using the eject air system or by hand with extreme care. 4. Feel for resistance. If the tube does not drop in smoothly, do not force it. Remove it and check for obstructions. Removing the tube, 1. Use the eject air system to raise the tube gently out of the probe. 2. Catch the tube by hand before it is fully ejected from the guide to prevent it from falling. Chapter 5, the console unit and peripheral devices. Chapter Objective, to describe the function and proper handling of the key electronic components within the AV3 console and its associated peripheral devices. Understanding these components demystifies the data pathway from the digital command to the analog RF pulse and back to the digital signal. 51 Radio frequency, RF, generation and reception. This section details the signal pathway through the console, from command to acquisition. The digital to analog, DAC, path, transmit. 1. TopSpin command. The user enters a command like ZG. TopSpin calculates the precise digital waveform for the desired pulse sequence. 2. Synthesizer, SY, and frequency generator, FG. These modules generate a stable, highly precise RF carrier wave at the exact Larmor frequency required for the nucleus, e.g., 60,013 MHz for superscript 1H, 3 pulse shape generator, PSG. This module takes the digital instructions from the computer and the carrier wave from the FG. It digitally creates the specific shape, duration, and phase of the RF pulse, e.g., a square 90 degrees pulse, a shape selective pulse. For digital to analog converter, DAC converts the digital waveform from the PSG into a low-power analog voltage signal. 5 RF amplifier, TX amplifies this low-power signal to high power, e.g., 50W for superscript 1 superscript 3C, 100W for superscript 1H. This powerful pulse is sent to the transmit/receive switch 6 duplexer. In the probe, this switch protects the sensitive receiver by routing the high-power transmit pulse to the coil and then instantly switching to allow the weak NMR signal to pass to the receiver after the pulse is finished. The analog to digital, ADC, path, receive 1 preamp. The extremely weak signal, microvolts, from the probe is first amplified here, critically, with minimal addition of electronic noise to receiver, RCU. The signal is mixed down to a lower, manageable frequency, filtered to remove unwanted noise, and then 3 analog to digital converter, ADC digitized by the ADC. This converts the analog voltage of the free induction decay, FID, into a digital number that the computer can process. For digital signal processor, DSP filters and processes the digital data before sending it to the workstation for Fourier transformation in TopSpin 52. The preamp, function and handling precautions. The preamplifier is a small but supremely important box located very close to the magnet, often mounted on the console rack or the magnet itself. Function, to provide the first stage of amplification to the nanovolt level signal coming from the probe. Because it is the first amplifier, any noise it adds is also amplified by all subsequent stages. Therefore, its primary job is to be an ultra-low noise amplifier. Its quality is a major determinant of the overall system sensitivity. Handling precautions: never power on/off with RF connected. The preamp is extremely sensitive to voltage spikes. The console should always be powered on before connecting the RF cables from the preamp and powered off after disconnecting them. Modern systems often have interlocked cables to prevent this. Avoid static discharge. Handle the RF cables with care to prevent static discharge into the preamp inputs, which can destroy the sensitive transistors. Physical protection: do not drop or subject the preamp to physical shock. 53. The automatic sample changer, BACS 60 or sample jet. An automated sample changer dramatically increases throughput and allows for unattended